Hej och välkomna till denna installationsföreläsning som Gabriel Sas ska hålla i ämnet byggkonstruktion. Jag som står här, jag är väl någon form av ordförande här under den här presentationen. Och jag är då Mats Näström, prodekan vid den tekniska fakulteten vid LTU. Och installationsföreläsningar, ja, det är någonting som vi genomför varje år. Och de hålls av de nya installerade professorerna. Och de installerades då i år den 13 november vid den akademiska högtiden. Då de fick ett diplom och lite andra roligheter, äta lite gott och så. De här installationsföreläsningarna, de har vi också för att vi ska kunna få någon form av inblick i forskningen som våra nya professorer gör. Och det är både grunderna och även höra lite grann om forskningsfronten. Föreläsningen den kommer att ta cirka 40 minuter, det kan vara plus minus någonting där också, men däromkring då. Gabriel kommer snart att få presentera mer om sig själv, men titeln på presentationen den har ni här på skärmen, den är ju på engelska där, men på svenska är den hur kan vi bygga säkert utan att äventyra miljön för kommande generationer. Det handlar om hur vi kan designa nya strukturer som är återvinningsbara eller har en mycket lång livslängd utan underhållskrav. Gabriel kommer också föra en liten intressant diskussion huruvida konstruktionsingenjörens roll, om den blir avgörande för att främja hållbarhet genom ett nytt koncept som kallas hållbarhetsmedveten konstruktionsdesign. Så, Gabriel, varsågod.
Tack så mycket Mats. Min mikrofon funkar bra. Hör ni mig? Vad bra. Så tack och välkommen alla. Jag tror vi har många gäster också från utomlands också. Det är många som är online utomlands, så kanske vi kan byta den på engelska om det är okej med alla. All right. So starting up with the question, right, that Mats has stated and you see it on the screen. One of the most important things that I think for the future is to find the answer to this question of sustainability. And the answer for us is sustainable conscious structural engineering. This is the answer that we have at LTU when it comes to all the built environment. Now, let's look a bit at defining these terms, sustainability and structural engineering. We have been talking so much about sustainability in the last years, you know, the Greta effect, the Friday, what was that called, when she was taking some leave from school, and all the questions that are emerging around how we are protecting the environment. So, talking about sustainability, we are looking at first etymology, the definition. Sustainability is a noun, and it's very often used in conjunction with the word sustainable, which is an adjective. And sustainability is derived, or sustainable is derived from the Latin word sustinere, which is a verb, which is built of two other words, which is, the first one is tenere, to hold, as you have the hand there in the picture, and sub, which is under, to hold under something. That means sustainable. And then there are some definitions of this sustainable concept, and I found two of them that are quite maybe easy to understand. There are more that are more complex, and they're from the Cambridge Dictionary, one of them, the first one that you're reading there. And the second one is from Merriam-Webster. So in a very simple put word, let's say like this, is to able to continue over a period of time. That means sustainable. And we started to be aware of these challenges with sustainability sometimes in the 80s, when the United Nations has set up a commission called Brundtland Commission, which the name Brundtland comes in fact from the chairman of the commission, who was by maybe, it's a Scandinavian lady, she was the Prime Minister of Norway. And she has actually put up a report together with her team called Our Common Future in 1987. And then we defined the first time sustainability, what it means for us as nations. And sustainability means meeting the needs of present without compromising the ability for future generations to meet their own needs. What do we leave after us to our kids that they can actually leave something to their kids and so on? Now, at the same time, they defined also 3 strong pillars of sustainability. Sustainability deals with economy, society, and environment. And here we have a lot of potential other characteristics besides the words that I put for each category there. And then, as you see, this is not maybe a very balanced picture, but this is what we are striving towards. Finding the equilibrium between these 3 parts: economy, environment, and the social aspects. The correlation between all of them are overlapping at the parts where they are in contact, let's say. So for the environment, it's important that the economy and the environmental relation should be viable. The environmental and the social relation should be bearable. We cannot increase the number of population to infinity. It's not going to be possible for the Earth. We have to do something about that. Maybe move to space, right? This is what Elon Musk is looking at today. Then, of course, one of the challenges is the equitability. How fair it is to everybody to have, as it is today. I think the last report shows us that I think 5% of the population earns more than 95% or 95% of the whole wealth in the world. That's not equitable, probably, right? So in an ideal world for us, it would be a balance. All these circles should be the same, should have the same size, and should be in a way driven by the same desires to be sustainable, right? And this is the theory. But then we have the challenge, which is today. We are focusing a lot on the money, on the wealth, on economy, on making profits. And that is in detriment of the social part, but more now than ever since the pre-industrial or since the industrial revolution, on the environment. And we start seeing these signs. So our challenge, mine, yours, and especially to our students that are sitting here, because you are the future, to put it like that, when it comes to structural engineering and everything that we will do, is to change this mentality. We need to be sustainable conscious, and in whatever area of work we are, in whatever part of our life we are. So, with that being said, the United Nations have produced this report, but they have also produced actions. They say like, okay, these are our goals. We have 17 goals that we have to work towards in order to be sustainable until 2030. This is something that is called Agenda 2030 in Sweden, the Sustainability Development Goals in other countries, and so on. And the reason also for that is mainly because the environment, there are a lot of environmental challenges that we were not aware of until very recently. And this graph shows you what has happened with the carbon emissions since the industrial or the global start of the industrialization in the world. What you can see on the vertical axis is the contribution of oil or petrol, coal, natural gas, cement production, and gas flaring in the atmosphere we have. That is something that is measured when it comes to CO2. But there are also other emissions that we are talking about. The methane emissions. So everything that is related to carbon. So there is a lot of debate of course. It can be like, people say global warming, it's an effect of the industrialization, but it can be also just a cycle of the Earth. But nevertheless, it is an effect, and there is something that happens there. It can be both, it can be one, it can be the interaction, one more than the other. So I would like you to think a bit about and reflect upon your individual carbon footprint and mine. I have done that. So I would like you to do an exercise with me. Please take up your mobile phones. Some of you already know the answers to what comes next, but you go to this link that you see at the top of the screen and follow the instructions. Go to menti.com, use the code that you have there, and people I tell you that have done this with me already before this exercise, please don't spoil the surprise. And vote, thinking, I'm asking myself, I produce less carbon footprint if I do not fly to New York once, only one way, okay? I do not produce I produce less carbon footprint if I do not eat meat, drink beer, have dairy products. And I stop driving, or if I stop driving my car for 1 year. And I wonder if has anybody submitted a vote? Because I think it should update automatically. So maybe I should just jump a bit out and try to reload it. You missed the code. Okay. Let's try to get it back. But it seems that my presentation, it's disconnected from the web in this case. So no, now we have results. And I will get back to that. Let's see. Well, I can bring up also directly the result, the part where it's visible what we have. So the code again, it's there at the top, and people online can vote also, I guess. Wouldn't be a problem. So I think we have quite many answers now, 29 in total. That's very good. We are also making some statistics on that because we have some results from previous presentations, so we are testing a bit or doing some investigation. I think it's good. We have basically a good understanding of the majority of the votes. So now I will try to get back to my previous presentation and present you also the results. So moving back there and looking at results. If we do not drive the car for 1 year, we can save 3 tons of equivalent carbon footprint. So that was the most impacting activity. And we will get back to these slides or to this information in a bit, in a few minutes. So remember these numbers. You are saving 1 ton of CO2 equivalent if you do not fly to New York. You are saving 2 tons if you do not eat meat, you do not drink beer, and you do not eat dairy products. So that's kind of like a tough life, I would say. I mean, for all of us that are enjoying that part. And then, of course, if you don't drive your car, that is fossil fuel car, then you would save like 3 tons of CO2 equivalent. So far we discussed about sustainability. I tried to get an introduction and a definition of the sustainability from the perspective of what we are seeing it, or how we are seeing it today, or how I interpret it also, in a very brief manner. And now let's talk a bit about structural engineering, because I think structural engineering, it is something that, especially in Sweden, there is a difference in concepts, I would say like this. For me, it was a bit, let's say, confusing at some point in time. Structural engineering, it's a branch of civil engineering, but in Swedish, I think we have civil engineers are also economists, in a way, civil engineer, if you're looking at that. So I said like, okay, let's try to understand what structural engineering is. And I would say like this, that it is a branch of civil engineering which deals with the analysis and design of structures. And that means like, how do we calculate how much capacity a bridge has, or this beautiful building? If you're looking at it, this is an amazing building with a high span, with two main arches crossing the roof, and then you have some beautiful windows there and open space. I don't know if anybody has checked this before, but I was amazed this morning when I seen it, how beautiful it can be. And we are, as structural engineers, we are applying normally mathematics and physics to solve some problems that are, let's say, of abstract nature in many ways. I would say like this. We are making some simplifications, we are putting them on the paper, we are creating some diagrams, and then we are understanding how the forces are flowing to a structure. So, for that reason, structural engineering, it's an applied science. And it is also an applied research area. We need to collaborate with other disciplines in order to make use of our results for them, or us using results from material science, for example. So let's put it like this also. The aim of structural engineering at the end is to facilitate the structural design or analysis so that structures are safe, serviceable, we mean by being able to use them, and durable. We cannot build a house like this and then we have to replace it in 10 years, right? That's not durable. Now we can call it not sustainable also. And structural engineering, it's part of a bigger process during the life cycle of structures. So we have here like 5 main categories that we are discussing about. Is like when we are building something. So we have the planning part of the building. We have the structural design, which is the main core of structural engineering for us. We have the production technology, we have the exploitation, and we have the end-of-life demolition and recycle and reuse of the structures. This is a linear model, as we would call it, of having structure from cradle to grave. And for us, structural design and structural engineering is in the second leg, very important, but also we are working a lot in the exploitation phase, by assessing the performance of structures, understanding how much they can still carry after 100 years of being built, how much loads can take. So let's look a bit at some example of some structures. I think this is important because I think maybe this gives us also an idea of the importance of this work to our students here. What has been built during the recent, maybe 2,000 years, I would say like this even. Golden State Bridge, built in 1937. A beautiful monumental piece of architecture and engineering. Tensta, Stockholm, apartment blocks. The Miljön Programmet, I think, built 1965 to 1974. Pantheon in Rome, 124 before Christ, 2,000 years and some. Eiffel Tower, very beautiful structure, right? What about this bridge? Pontus Fabricius in Rome, 62 before Christ. Very old bridge, 2,000 some years, huh? The first nuclear power plant, built in Russia. My wife is Russian, so she's proud of that. And something very recent and very monumental in a way, Burj Khalifa in Dubai, 2010. So, I would like to ask you, why do we look at all these structures? Why do I choose these structures, right? Is there a specific reason? And I say yes, because in all these structures there is a value of some sort. And value for structures, we can define it in monetary value. You have an apartment building from the milieu programmet, has increased, maybe, the price or not. Very likely. You have Burj Khalifa, which is a building that has a lot of value, not only monetary, but also cultural value for Dubai. The Pantheon, the same. It is a cultural and social value. So most of the built environment, most of the buildings we are using today are having a specific value. And the more values you see from these 5 categories that we are having here, the more important they are for the whole world. Like we look at the nuclear power plant. Actually, it has monetary value because it produces electricity. It has environmental value because it's substituting maybe other ways of production of energy that would be more polluting. The Golden State Bridge, it has a use value. That's the main purpose of the bridge. You have to cross over it, but it became also a cultural value. Everybody knows about it. I mean, I talk about Golden State Bridge because I heard about it, and it's very beautiful, and I looked at it, right? So maybe with this part, I would like to say that I talk now about 2 different aspects. One is the sustainability, the other one is the structural engineering and what we are building, how they look together. But now, if we try to put them together, how do we do that, right? What is important? So I would like us to go back to this picture and look at it in a linear way as it is. We are doing planning when we talk about a new structure. We are doing some planning. We are doing, that is usually the client that has some wishes. Then we are doing some structural design. Then we are doing producing the structures. And then once they are there, then we start using them, exploiting them. And then suddenly we have to, okay, take them away, replace, and so on. This is a linear model, cradle to grave, as mentioned before. And the question here is, in all these processes that we have here, what is the impact we are having on sustainability? We do have 4 legs: product, construction process, use, and end of life. And in each one of them, we have different subcategories. And they were cataloged in an ISO standard. And I'm using the same terminology here just for the sake of simplicity, I would say like this. But important is to look at it. When you have a product from raw material, you need to excavate it, you need to transport it, and you need to manufacture something from that raw material. Then, once you've done that, you transport that raw material or that product to the site, and then you do some construction. And so on. Then you use the building, and then at the end you have to dispose of it. And then recently we started thinking also about what happens beyond the life cycle, right? So that's the 5th leg. And now when we are thinking a bit about the impact of all this process on the environment, I'll show you some numbers. The ones at the bottom. I didn't find a better way to put it, unfortunately, but I hope it's readable, and I think it's readable. 50% of the CO2 equivalent is produced in the production phase, not even getting started the construction. 5% goes to construction process. This is how much we are using. And then we have 20% in use, the B1 to B5. But then, surprise, we have also something else there, a 23% for the energy that we are using to keep operating those buildings. Like here, we are not freezing because there is some energy that we are putting in here to warm up, right? And then end of life, it's only 2% that we are consuming. So, just to sum up that part, that is how much we are influencing the full life cycle. 50% of all extracted materials go to the buildings. 50% of the total energy consumption goes to the buildings. 30% of the water goes to the buildings. And then we are generating 30% of all the waste in the world. It's a lot. But then there is a solution also, I think. Or something that we would like to provide. And we working here at LTU in the Structure and Fire Engineering division, we are considering this. So we took all these categories and we look at it in a way like, how about we can try to create an infinity loop in construction? So we would start from A1. My pointer doesn't work on the super white screen there. And we go around, and then we try to optimize the processes, and we try to actually get back to raw materials, but maybe skip extracting more, or transporting, or manufacturing, or transporting on the site. And we are just ending up at the construction phase already. And in that way, we would say 55%. So what this tells us, or me at least, is instead of building something new, let's try to keep what we have now in use. Because we can save up to 55% of the carbon footprint. Lars, you're not very convinced. So when we're looking also a bit at the potential of the structural engineers, like the new generations we have here, how do we, I'm considering myself very young, and we have also these generations here that are super young, and I'm so proud that you are here with us today. And it's very important maybe for all of us to acknowledge that. In the building process, and according to some research done by the Order of Architects in UK, they have evaluated how much we can actually reduce the carbon footprint at different stages based on each profession's role. So if we are working with strategic definition, which usually is the client and maybe a lawyer or somebody that is working with a manager, then of course you can still do many changes. You're still at 100%. You can change the building completely. You can do something else. When you're looking at preparation of briefings and concept design, you already have decreased by 20%. So you're 80%. You can still change or influence the carbon footprint. And us structure engineers are at stage 3 and 4. So up to that point, we can reduce by 50% the carbon footprint. So maybe let's look at some numbers, because I know there's like a lot of talk about very beautiful graphs, but let's see what it means in numbers also, right? So if we're getting back again to our beautiful exercise of understanding what is sustainability and how much carbon footprint we are producing, I would say like this. If, as a structural engineer, I manage to reduce by 20% the embodied carbon during a year, and the research is done on maybe the average of, let's say, a structural engineer designs about 5,000 square meters, and for activities that are let's say, connected to raw material extraction and construction, we can account for that about 200 kilograms per square meter. And then if we reduce it by 20%, that's how much we could save. It's 200 times more than flying to New York, or 100 times more than not eating beer. So we can continue eating beer and eating meat and drinking beers and having milk products in our diet. And another question that popped up in my mind was like, okay, when I was doing some research about this, was how can we do this in practice? So another research done by Instructive, which is the Institute of Structural Engineering, tells us how this can be done. And I will let you read these things. I think it's not important for me to go through this, but I specifically like to highlight something there, which is called build less, build clever. Those are the most important things, I think, from my perspective also. But these are ways, these are means that next generations of structural engineers can influence the environment. I think we are good, right? Most of us got through it. So for those of you that are not that familiar with the subject, is maybe the first column is very important. The rest is, it's more like, details of how this can be done. But for our students and for us that are working in this field, I think all of the levels are important, but there are just some examples there too. So now narrowing down a bit our mission at LTU in our division of structural and fire engineering, and mostly for the work that we are doing in structural engineering, was a question that I asked myself: how can we contribute as a group? What would be the thing that our group would work with mostly in the future? So then we had some discussions, some workshops, some ideas, and then we came up with a concept that we call it true capacity. And then if we would like to extend the life of structures towards, of course, the aim to have sustainability, the last part of the text there that you would see, then we would like to work in a synergetical way with three main areas. And this requires multidisciplinary work because we can do tests of different nature, from small-scale tests to testing materials, or to testing bridges, or to testing just beams and so on. But we have to also record the data that we are calling structural health monitoring. We need to know what we are doing there, and we need to measure the data and then make sense out of it. And then also we can extrapolate the results by doing simulations. We can use this as a benchmarking, the test that we are doing, and then we can extrapolate towards maybe more generalizing, creating some new concepts for that. And then, of course, we have to measure what we are doing in a way, so then we are using the outputs, and there are some different methods there that we can use for doing that. And then to quantify what we are actually, if we are achieving some goals towards sustainability. And now we know that we want this 20% at least reduction, right? So we can all work with all these areas. And of course, for us, it's important to work towards the sustainability development goals, which are, we said, like the education is very important. We have a mission as a university here to educate, right? This is the primary reason why we are here. Then we need to work towards producing and helping produce decent work and economic growth. We need to work towards industry, work together with industry and provide options and solutions for innovation. We need to look at the responsible consumption, of course, as mentioned, and participate in all other activities that we are or could be at the end invited to participate in or collaborate with other, let's say, disciplines. And activities that we are planning to work with, or and have started working with maybe for many years, are some of them, but some of them that we have not yet, but we will in the future, are these three that we are looking at. Life extension of existing buildings and infrastructure, and that's something that our research group has been very strong in the years to working with. But we need to look more into better materials and design methods to build for many generations. We need to be better at predicting the true capacity of the buildings and any structures. And then we need to find ways to optimize resources and the resource utilization. And maybe some examples of the activities, and these are activities that spanned in the last maybe 30 years, I would say, at LTU, and they are related to bridges. So what we have done in our, let's say, thoughts of finding out what is the true capacity. We have tested many bridges, 14 of them, as I counted. Maybe Lennart, you know there are more or less, I would say, we are there. And then we are in the process now of preparing 2 more tests, or maybe 3, if we say like one is a double test there. And the whole idea of this test that we did, we tested these bridges to see how much more load we can put on them and still use them. We're testing these bridges also to know also how much they could hold if they would have been in use. And always the conclusion was like, they can hold more. 14 plus, I would say like this. There was always extra capacity in them for the purpose of the test. So the question is then, why should we demolish them? Why did we demolish them, some of them? And there is no direct answer to that question. I think it's more a matter of understanding and balancing all the aspects that are related to those specific bridges. And now, currently, we are looking very deeply into the whole bridge population in Sweden. And we understood that there are about 16,000 bridges in Trafikverket's database. And then there are 4,000 railway bridges. And we are estimating there are about 10,000 more owned by others, which could be municipalities or private actors. One thing that we noted also is that the bridge stock is getting old and older, but the problem is that we are building faster than ever. So they are getting older, we are building faster. That's not a very good combination, because they are still going to get old, and we're going to have more older bridges. And then in addition to that, we have heavier loads. We want to transport more. The transport frequency is much greater than it used to be before. And now if we are putting on top of that the hazard in loads due to climate change, when we have some extremely, sometimes high snow loads, especially here, we talk about Norrbotten, then there are challenges that require from us a lot of more interdisciplinary and multidisciplinary work when it comes to the bridges. And in this picture you see, in both pictures you see Kalix Bridge, the one at the bottom, the one that will be replaced by the bridge that you see to your left, the new bridge. And then to the right is the existing bridge. The one to the left is completed now. This is a picture from the summer, I think, when we took this. And I would like to invite you to follow up on our project where we are going to test the bridge in Kalix to understand, the one that is going to be demolished, of course, to understand how, and maybe the main aim is to develop methods so we can apply them on other bridges to understand how much capacity they could hold in the future. So I think with this part, I'm very close to completing my presentation, and I would just like to make a short summary of this lecture about sustainability, conscious structure engineering, and how does this contribute into creating structures for the future without jeopardizing the environment. And maybe 3 takeaways for you. If there is something that I would like you to remember from this lecture, it would be this. We need to extend the life of existing structures. If we do that, we can save 55% of the CO2. It's not possible everywhere, and it's not going to be ever possible to save everything. But try to understand and find the value in the structure that you are working with. Second, design for circularity. Understand which processes are important in the CO2 emission or the carbon footprint we are living on the world. And third, which is more related to the work that we are doing, we want to develop methods to promote sustainability in structural design. And this requires collaborative effort. For everything that we are doing today, we cannot do it alone. This is a too big challenge for one person or for a small group. This is a challenge for the whole humanity. And I would like to thank you for your attention, and I believe that we can wait a bit for the questions, because I think Mats would like to say something.